Please start, sir. Okay, sir. Good afternoon, everyone. Welcome to the ninth session of this FDP. It is my great pleasure to introduce Dr. BABITA MAJHI, Assistant Professor, Department of CSIT, Guru Ghasidas Vishwavidyalaya, Bilaspur, Chhattisgarh. Dr. BABITA MAJHI is an accomplished academic and researcher with expertise in field of computer science, agriculture, image processing, and medical imaging. She has contributed significant research to image processing, machine learning, agriculture informatics, and medical data analysis. Dr. Majhi has published several research papers in reputed national and international journals and presented her work at conferences of high repute. With her dedication to teaching and research, Dr. Majhi has guided students in developing innovation solutions to real-world problems. She remains committed to advancing knowledge through quality research, interdisciplinary collaboration, and mentoring young scholars. Welcome, ma'am. Welcome to this session, and thank you for inviting. Thank you for accepting our invitation. And the session is yours, ma'am.
Thank you, sir, for giving a nice introduction of me. And I want to add to it that presently I am working as an associate professor in the Department of Computer Science and IT of Guru Ghasidas Vishwavidyalaya Central University of Bilaspur since 2023. I was promoted to associate professor. So
Okay, sorry, ma'am. So our data is old data.
Pravir sir, since he left our university, he forgot everything. Okay. So should I share my slides, sir?
Madam, please share your slide.
Okay.
Actually, I have class, madam.
Okay,
The problem.
okay, you can listen. I have to interact with the participants. How many participants are there, sir?
Now it is 56, ma'am. It will increase.
Sir, my screen is visible to you?
Yes, ma'am.
Should I check whether it is going ahead or not, or should I start?
Please check, ma'am, as you wish, ma'am.
Okay. You just check whether my slides are changing or not. Is it changing? Sir Pravesh, sir?
No, ma'am. No, ma'am.
So can you please check now?
Yes, ma'am. Now it is changing.
Now it is changing. Okay.
Yes, ma'am.
So good afternoon, everyone. I am Dr. BABITA MAJHI. I am very much thankful to Dr. Pravesh sir for giving me this opportunity for giving a presentation in this AICT sponsored ATAL FDP. So the topic of my discussion of today is healthcare and data analytics using machine and deep learning techniques. So actually this work is done by one of my PhD students who received her award or degree in 2024 only. So here I will discuss three major problems in healthcare. First of all, we'll discuss about how we can do the prediction of the mortality of those patients who are getting admitted to the ICU units. So the topic is wavelet-based ensemble models for early mortality prediction using the imbalance ICU data. So as the report of US, it was observed that 10 to 20% of the patients are dying in the hospital, and more than 5 million patients are admitted to the ICU every year. And the full form of ICU, everybody is knowing, it is intensive care unit. So when a patient is getting admitted to the ICU, so there are dedicated doctors are there, the nurses are there, and also in the ICU we are using very expensive equipments like the ventilators and other medical equipment. So all these things are involving a large amount of the budget for that particular hospital, we can say. And if we can do the prediction of the mortality of the patients who are getting admitted in the ICU, then it is very much beneficial for the hospital to manage the costly equipment, manpower, and the other resources also. That is the main objective of this resource problem. Can you do the mortality prediction of the patients who are getting admitted to the ICU within the first 24 hours or the 48 hours? That is our main objective of this problem. Next is I will discuss about what is the proposed methodology that we should use for its implementation. So we have collected the secondary data from the PhysioNet challenge, then the WITS datathon, that is Women's in Data Science, and from the Mimic 3 dataset. These are the very standard datasets which the people are mostly using for doing the mortality prediction. And once we collect the data, we find out that the most of these three data sets are having a number of problems in it. So what are the challenges within this data set? First is the missing value problem. More than 50% of the data are missing in case of the PhysioNet challenge and WITS data set particularly, and they are imbalanced data. And so first we have to do the pre-processing over the data. So when we are collecting a real life data set and we are finding that only 0.5% or 1% of the values are missing, in that cases we can ignore those tuple or the records. But if the number of missing value is more than 30%, 40%, 50%, then if we ignore those record or the tuples, then it is very much we are losing a large amount of information. So we are not going to get very good result out of the data set that we are going for doing the analysis. So first what we have to do, we have to do the imputation of the missing values. So in our approach, we have used the two methods. In one case, we have done the mean imputation, and for the other two data sets, we went for the KNN imputation. So in case of the mean imputation, what we are doing, if the missing values are there in a particular column, then you have to take the mean value of that particular column and we replace that missing value with that mean value. But in case of the KNN imputation, what we are doing, we are trying to find out the k number of nearest neighbor of that particular missing value, and we fill that missing value with that neighbors. And what is the imbalancing of the data set? That means in a particular data set, I am having, if I give an example of the data set having the binary class data, that is the positive class and the negative class data. And within the data set, if I am having the tuple of the records of a particular class in a large number in comparison to the record of the tuples of the other class, then we are saying that the data set is not balanced, it is in the imbalance form. And if I do the analysis with the imbalanced data set, what will happen? Our result will get biased towards the data tuples which are measured in the number. So before going for the analysis, what we have to do? We have to do the balancing of the data. Then we will do the normalization of the data. So here we did the normalization of the data by using the mean max algorithm. And then from the raw data, we have extracted the features by using the discrete wavelet transform. And then we have used the different 12 numbers of classifiers like KNN, SBN, decision tree, random forest, Navier, multi-layer perception, linear regression, and other TabNet, XGBoost, CatBoost, DataBoost, and the light gradient boosting algorithm to find out their performance. And once we find out of these 12 classifiers, which classifiers are performing best, then we combine those classifiers to develop an ensemble classifier model. And then we train the ensemble model by doing the 5-fold cross validation. And then we are doing the testing and the performance evaluation to it. Okay, this is the complete methodology that we are using. If I go for the data description, For the PhysioNet challenge, there are 12,000 records are there, and the total number of features here is 42. And out of these 42 features, we have considered only the 40 features for the simulation purpose, because in most of the real life data, when we are collecting, some of the columns are not very much relevant to our analysis purpose. For example, the patient ID number, the patient name, all these things are not relevant to us. So we are trying to exclude those data. So here we have used the 40 number of features for the simulation, and then we have applied the discrete wavelet transform over it. So as all of us are knowing, when we are applying the discrete wavelet transform over a vector of data, it will divide the data into two halves. So one is your low frequency component, another is the high frequency component. So in this way, so after applying the discrete wavelet transform, we obtain the 20 features which we are using for the analysis purpose further. And here the class number is only 2. And then we are dividing the data set into the training set and the testing set. So the training set is having the 80% of the data, and the testing is having 20% of the data. Similarly, for the WITS datathon, we are having 91,713 records out of, and it is having 188 features. And out of the 188, we are using 176 for the simulation purpose. And when we are applying the discrete wavelet transform over here, we are getting the 22 features when we use these 22 features for doing the simulation, and then we divide the data into the training and the testing purpose. Similarly, in case of the mimic 3 data set, we are having 38,597 tuples. So, what is our decision, which patients we want to include and which patients we want to not to include in our simulation? We decide on the basis of this criteria. In case of the PhysioNet Challenge 2012 datasets, only the adult patients whose age is greater than 15 and less than 90, and who are staying in the hospital within the first 48 hours, we are considered. In case of the WITS datathon, all the adult patients who stay in the first 24 hours in the hospital, that we consider. And in case of the mimic 3 data set, we are considered those patients whose age is greater than 16 years and who are staying in the ICU for the first 48 hours. And all the 3 problems I have already discussed. They are having highly missing values, they are highly imbalanced, and their dimension is also very high. So we did the pre-processing, as I told, we did the missing value handling by using the mean imputation or the K-mean imputation. And then we did the balancing of the data by using the SMOT technique. The full form of the SMOT is synthetic minority oversampling technique. And not only SMOT, we have used many variants of it also, like borderline SMOT, support vector machine SMOT, adaptive synthetic sampling SMOT, edited nearest neighbors SMOT, and Tomek link SMOT. Then we did the normalization using the mean max normalization technique, and then we did the feature extraction by using the discrete wavelet transform. Now let me explain what is the meaning of SMOT. So as I told, the full form of SMOT is synthetic minority oversampling technique, and it is a very popular method which is used to balance the imbalanced data sets. So what it is doing, without doing the duplicating of the minority class, it will try to generate some new samples or synthetic samples and try to balance the data set. So how actually it works? Let us, if I take a example of a binary classification problem. In the binary classification problem, we are having one majority and one minority class. Let us say the 0 class is the majority class and 1 class is the minority class. Then what happens? For each minority class samples, we have to find k number of nearest neighbors. If I specify the value of k is equal to 5, then for each minority sample, I have to find out 5 neighbors for it. And then we have to select randomly one or more of these neighbors. And then we have to draw a line between the original sample and its neighbor. And then we will choose a point along this line at random distance. And this new point will become the synthetic sample which will help us to balance the data set. If I take an example, so here you see, suppose we have a minority class sample at the coordinate value 2, 3, and one of its nearest neighbor is given by the value 4, 5, then the synthetic point can be generated by this equation, that is 2, 3 plus 0.6. This 0.6 is a random number. You can take any random number that lying between 0 to 1. So here I have taken the 0.6 into the nearest neighbor 4, 5 minus 2, 3, and if you solve it, you will get the value is 3, 2 and 4, 2. So this is the new minority samples that we have find out for the minority sample 2, 3, and in this way other samples also we can find out, and it will help us to balance the data set. So here what we did, as I have already discussed, we have collected the data, then we do the pre-processing. Under the pre-processing, we did the missing value filling, and then we did the balancing of the data, and then we do the normalization of the data, and then we develop the 12 classifiers, and based on the best performing classifiers on the base of area under curve, we selected 3 models and then assemble them. So for the PhysioNet challenge data set, so we have selected XGBoost, CAT boost, and light gradient boosting to ensemble. And for the width data set, we have used the random forest, XGBoost, and the CAT boost. And on the decision of the majority voting, we are selecting what should be the predicted output. So these are the hyperparameters that we have chosen for doing the simulation. And these are the performance measures. These are the very common performance measures: sensitivity, specificity, precision, F1 score, accuracy. But accuracy is always, I cannot say it is the only one performance measure which showing that whether the classifier is performing or not, or better or not. So we are going for the most important performance measure when the data is imbalanced. We are using the ROC curve or the AUC value. So these figures are showing the performance measures for the SPM classifier with the PhysioNet challenge data set. And here, if you observe very minutely, under every performance measures, I have written the mean and standard deviation. So why it is written? So when we are doing the simulation experiments, and only by doing a single experiment or single round, if I am saying my model is performing very well and it is giving this result, that is not always correct. So what we have to do, we have to do 10 or 20 times independent experiment. We have to run the programs independently 10 times or 20 times or 30 times. And then you have to find out the mean value and the standard deviation of the result that we are obtaining. And that value we have calculated and specified in this table. So here you see, for the PhysioNet challenge dataset for the support vector machine, it is with the ENN SMOT value, SMOT balancing technique when you are using, it is giving the better result of AUC, that is 0.785. Mean value is 0.7815 and the standard deviation is 0.01. Similarly, for the other classifiers also, we have mentioned the values, and then depending upon the best AUC score, we did the ensemble models. We take the decision how to do the which models to be participated in the ensembling techniques, and we decided the three models for assembly for all the 3 data sets. So skip all these things, it is not required. It is only the results that I have added here. So here you see, in case of the PhysioNet challenge data set, we ensemble the XGBoost model with the BD SMOT, and then the CAT boost model with the ENN SMOT, and the light gradient boosting model with the ENN SMOT. And it is, when we do this ensembling, our area under curve is coming to 0.9266. And this ROC curve is also displaying the value. And this ROC curve, basically, it shows the trade-off between the true positive value and the false positive value. And here we are getting the value of area under curve as the 0.93. Similarly, for the width data set, here we ensemble the BDS mode and the random forest, ENN's mode with XGBoost and ENN's mode with the cat boost. And here also we obtain the AU shift value as of 0.944. Similarly, for the Mimic 3 dataset, we combined the ENN's mode random forest, ENN's mode XGBoost, and ENN's mode cat boost. And here we obtained the AU sheet value as the 0.98. And we compare our results with the already available literatures, and we find out that our results is performing better in all the 3 data sets. And after doing the experimental simulation experiments and adding the results, sometimes the reviewers are commenting why you have done only the simulation based results and why you have not done any statistical test to say that your results are actually they are correct and they are significant. For that, we go for the pair t-test, and under the pair t-test, you have to first decide a null hypothesis. And here if the value of h is equal to 1 and the value of p is less than 0.05, then we can say that the two models between which we are doing the comparison, the significance is the difference is significantly more. So here for all the 3 data sets, we have did the paired t-test, and in most of the cases we observe that our proposed method is very much significant in comparison to the other models. And all these results we published in a journal of smart health elsewhere, and also we filed a patent. It was published and now it is under review for granting. It is an Indian patent. And next, if I go for this mortality prediction, we have used the deep learning approach also. So what is our proposed methodology here? We have collected the data, that is the PhysioNet challenge data set and the WITS datathon 2020 data set. Then we did the pre-processing over here. All the pre-processing are sent. You have to do the missing value for handling, and then we have to balance the data set and the feature extraction. And then here only the difference is that from the previous research, here we're trying to find out the performance of the 3 different balancing techniques like SMOT, CSL, and the GAN. And then during the selection of the classifier, instead of using the machine learning techniques, here we have used the deep learning technique like the deep neural network, deep LSTM, deep bi-LSTM, and deep gated recurrent unit for as the classifier. And then we do the training of the model using the 5-fold cross validation, and then the testing of the model, and finally we do the performance measures. So SMOT I have already discussed in my last discussion. So now we'll discuss what is the meaning of cost sensitive learning and how it will be useful for the balancing of the data set. So cost sensitive learning, or CSL, it is basically deal the class imbalance by assigning the different misclassification cost to different classes. That means what it will do, it will not do any oversampling or undersampling, but it is trying to penalize when the model is do the wrong classification, or for modifying the how mistakes can be penalized. So how it works? So in the traditional classification, all misclassifications are treated equally. But in case of your cost sensitive learning, what we are doing, we are trying to assign a weight for a misclassification. So what it is happening actually, for example, false negative might have a higher cost in medical diagnosis. When we are going for a medical test, and if it is positive and our classifier is saying it is false negative, then it is a big mistake in our side, and how we can. So here we are assigning a large weight to this type of error. Similarly, false positive might have a higher cost in case of the sperm detection. So commonly the cost of a false negative on minority class is set much higher than a false positive because missing the minority is more harmful. Then what we are doing, we modify the conventional cost function or the loss function by including the weight value. So here the loss function will be the summation of the weight value into the error function. So, and we will assign the value of the weight as a larger value for the minority class. Then we do the training of the model, not to minimize the error square, but to minimize this weighted loss function, and then we do the evaluation. So in case of the CSL model, here we don't have to do any kind, we don't need to generate any synthetic samples, etc. It directly works on the original data set, and it tries to correct the errors that is happening, or it is correct the errors that will happening by the model. So if I take an example of a binary classification problem, let us say the minority class is a disease class and it is positive, and the 5% of examples are there. And in the majority, it is the healthy classes are there, and negative class 95% of tuples are there. So in this case, if you want to assign the weight, then for the healthy classes, we'll assign the weight equal to 1, and for the disease class, we'll assign the weight is equal to 19. So how this figure 19 is coming, we are taking 95 by divided by 5, so it will be 90. And then we'll use this weighted loss function to as our cost function instead of the traditional cost function that we want to minimize. So in this way, the CSL will work. The next balancing technique is your GAN. The full form of the GAN is Generative Adversarial Network, and it is a deep learning framework which is designed to generate the new data samples. And GANs were originally developed for generating the realistic images. They have become a powerful tool for data balancing in imbalance classification problem. It is actually use the neural networks approach, and it consisting of two main components. One is the generator and another is the discriminator. So what the generator will trying to do, it tries to create a fact data that looks very much similar to the real data, and the discriminator will trying to distinguish between the real data and the fake data that is obtained from the generator. And if we, so how it works, the GAN, how it will do the balancing of the data. So first, we will take only the minority class data here. We will not consider the majority data. We will consider only the minority class data. And then the generator will learn to generate the fake data, and the discriminator will try to differentiate between the real data and the fake data. And when we go on doing the training of this, at the end, it will generate the synthetic minority samples, and it will be added to our original data set, augmented with the original data set, and our data will become balanced, and further we will use for the simulation purpose. So now this slide is showing what are the different hyperparameters we have used for the deep learning approaches. So if you observe here, the deep neural network and deep LSTM hyperparameters I have written. Here 4 layers, in both the cases we have taken 4 layers, and the number of neurons are also same in all the 4 layers, and all other parameters are also very much same, because when we are doing the comparison between the different models, then the situation or the environment of the simulation must be same. Otherwise, we cannot say it is a fair comparison that we are doing. Similarly, for the deep bi-LSTM and the deep gated recurrent unit, we have also tried to keep all the hyperparameters as same. Now, this table is showing the performance measures for the VisionNet challenge dataset. Here you see, here the deep neural network approach with the smart data balancing technique is performing better, is giving the AUC of 0.76, but the deep LSTM is performing better in comparison to that, and the AUC of 0.80. Similarly, if we go for the deep bi-LSTM and deep gated recurrent unit, here also the smart technique with the deep gated recurrent unit is performing better with the AUC value of 0.80. These are the ROC curves that showing the AUC that we have already displayed in our tables, and these are the results for the WITS data set. And here between the deep neural network and deep LSTM, the deep LSTM is performing better in comparison to deep neural network. And if I see overall, then deep bi-LSTM with a SMOT is performing better with the AUC of 0.87. And these are the ROC curves, which is displaying it. And we did the comparison of our proposed method with other reported literatures, and we have observed that our proposed it is performing better. Next topic that I am going to discuss is the Parkinson disease. So, what actually the Parkinson disease is? Parkinson disease, it is a neurodegenerative problems, and it is mainly occurs in the oldest people. And what are the side effects of the Parkinson disease? Since it is associated with the neurons that is present in our brain, the patient who is suffering from the Parkinson disease, it may lead to the dementia problem. They are having sleeping disorders. They are having they will face problem while walking. They cannot write the characters because they are they are having difficulty while writing because their hands are shaking, and another day to day for doing all the day to day activities also they are facing lot of problems. So our the problem with the Parkinson disease is that it is very difficult to identify that the patient is having the Parkinson disease at the early stage. If we can detect the Parkinson disease at the early stage, then it can be treated properly, and so that the patient cannot reach to a extreme level of its condition. So what is the methodology that we have used here for the early detection of the Parkinson disease is the data set is MRI data set we have used MRI images. So it is freely available from the PPMI data set. So two data sets here we have collected. One is your T1, T2 weighted data set, one other is your SPECT data set. So T1, T2 weighted and the SPECT data scan MRI images. So two data sets we have collected the MRI images. So once we collect the MRI images, then we did the pre-processing over it. So what type of pre-processing we did over it? So from its original format of the DCOM, we convert it to the .jpeg file format. Then we remove the empty titles if any is available. Then we crop the images so that we can exactly keep the MRI pictures. Then we strip the skull images and then we did the batch normalization. So once we did the batch normalization, then we divide the data into to have 80% and the 20%. So 80% of the data we use for the training and 20% of the data we use for the testing purpose. Then we train the proposed deep learning models, and the models that we have used here is VGG16, DenseNet, then DenseNet and LSTM, and Inception V3. And finally, we have proposed a hybrid model that will combine the VGG16, Inception V3. And here, instead of using the optimization of the hyperparameters conventionally, we have used a meta-heuristic algorithm named as Gray-Wolf optimization to uh, do the optimization of the hyperparameters of these deep learning models. Then we do the testing of the proposed deep learning models, and finally the results are set, the performance measures are calculated, and we evaluate its performance. So in the MRI data samples from the PPMI, the two set of data set here we have used. One is, as I told, it is T1, T2 weighted MRI images, and another is your SPECT data set. So total number of patients under T1 and T2 weighted, we have considered 30 patients, and out of the 30 patients, Parkinson disease patients are 50, and the healthy patients are 15. And we out of after this 30% to this 30 number of patients, we divide it into 80% and 20%. So for 20, data of the 24 patients we used for the training, and for the 6% data we kept for the testing purpose. And the total number of image samples that is used for the simulation in case of T1, T2 weighted MRI images is 9,070. Out of these, the Parkinson disease images are 3,620, and healthy patients are 5,450. Similarly, in case of your SPECT data set, we considered the patients, 36 patients. Out of this 36, 18 patients are having Parkinson disease and 18 patients are healthy patients. And we divide, when we divide it into 80 and 20%, we take 29 patients for training and 7% for the testing. And the total number of MRI images available is 20,096. And out of this 20,096, the Parkinson disease images are 5,752, and healthy images are 14,344. And then we divide it into 80% and 20%, and training samples and testing samples, and we did the training of the model. So out of the number of patients data available, we have selected only the 30 patients data. So what is our criteria of including only these 30 patients? So those patients are included in the study whose age is between 55 and 75 years. Only the Parkinson disease and the healthy patients are included, and the patients whose age is less than 55 and greater than 75, we did not include them in our study. So this is the MRI image that we have taken. So the image under A, it is showing the Parkinson disease image, and the image under B, it is showing the healthy patient object. And then we did the resizing of the image resizing, and the skull stripping. The figure under A is showing the grayscale image, and the lower person is showing the color image of this. Then this is the model that we have developed for doing the early prediction of the Parkinson disease. It is again a binary classification problem, whether the patient is having Parkinson disease or not. So 1 and 0, only two classes data is there. So we have developed the VGG16 model, whose hyperparameter is optimized by using the Gray-Wolf optimization. Similarly, another deep learning model, DenseNet, and its hyperparameter is also optimized by using the Gray-Wolf optimization. And DenseNet and LSTM, the combination of DenseNet and LSTM, and its hyperparameter is also optimized by using the Gray-Wolf optimization, and Inception V3, whose hyperparameters are also optimized by the Gray-Wolf optimization. And then we develop a hybrid model where we combine the VGG16 and the Inception V3, both the models we have combined. So what is the methodology for it or the architecture for it? So first we have collected the data. Its size is 224 plus 224 plus 3, 224 row and 224 columns and 3 because it is of the color image. Then we are applying it to the VGC16 block. The VGC16 is a we can say it is a modification of the convolution neural network having multiple convolution layer and the max pooling here we have used. And once we did this 5 times, we are doing the 5 convolution layers are there and the max pooling layers are there. And at the end, out of the VGC16, the size of the output that we are obtaining is having the size 7 plus 7 plus 5, 512, and then it is given to the inception V3. Inception V3. So here it is having inception and reduction block. And once it passed through it, then we are having the output. The size of the output is 7 plus 7 plus 6, 40. Then it is entering into the block 3 where another inception reduction is done. And finally, we obtain the output which is having the size of 3 cross 3 cross 832, right? And then we'll do the flattening of this information and we'll get the value is equal to 1024. And now this 1024 value will enter into the fully connected layer and it will decide whether the input that we have given belongs to the Parkinson disease patient or it is a healthy patient. So it will do this is the complete architecture that we have proposed for the early detection of the Parkinson disease. And these are the different parameters that we have used. The conventional manually tuning parameters are given, and also the learning rate, batch size, and momentum, dense unit, and epoch that we have used for which are optimized by using the gray wolf optimization are also mentioned here. So here is the results. If we go to the result, then we can see in case of our hybrid model, in most of the cases, our AUC ROC is having 99.67 value. In all the cases, VGC16, DenseNet, and LSTM, and Inception V3 also. But when we are doing the hybridization of the VGC16 and Inception, the AUC ROC is become 99.99 for the T1, T2 weighted data set. And similarly, for the SPECT scan data set also, here the AUC ROC value is also, in case of our hybrid model, it is equal to 99.92. It is a little bit less, I can say, in comparison to the VGC16 model. And here we did the comparison of our proposed model with the existing model. In case of the T1, T2 weighted data set, the proposed model is performing better in comparison to the other existing models that of the authors which was published in the year 2021, 22, 23, 19, and 18 by the different authors they published. And similarly for the SPECT data scan, here also our proposed method is almost giving the AUC ROC of 99.92, which is much better in comparison to the other authors who have published their paper in 2022, 2021, and 20. So this is the results that we have obtained. And finally, we get this published in the Journal of BMC Medical Imaging. That is, it is a journal of the SPINJET. The next one, the next problem that I am going to discuss is it is about the explainable driven machine learning for heart disease detection using the ECG signal. So according to the WHO, almost 17.5 million people are dying every year due to the heart diseases around the world. And this death rate is going on increasing day by day. So detecting the heart disease is very difficult at its early stage. And most of the people nowadays, the young people are also suffering from the heart diseases. It is because of the we are not able to detect at the early stage. And it is because of the lifestyle of the people, their eating habit, whether they are doing exercise or not, all these things are affecting our life. And most of the young people nowadays are also affected by the heart diseases. So what is the method that we have proposed for detection of the heart disease from the ECG signal? We have chosen the ECG signal. What is the reason behind it? So for detecting the heart disease, there are many tests are there prescribed by the doctors. Like your echo test is there, the TMT is there, and other tests are there. But ECG is a test which is generally prescribed by the doctors. It is very cheaper and it can be done very easily. That's why we are considering how we can detect the heart disease of the people by using the ECG signals. So here also we have collected the secondary data from the three different standard data sets. That is the PhysioNet challenge, then the Pascal challenge, and the MIT-BI data set. Once we collect the ECG signal, then what we did, we try to do the pre-processing over the signal. So we do the pre-processing by passing it through the bandpass filter. Then we did the zero phase filtering. Then we did the denoising of the signal by using the discrete wavelet transform. And then the reconstruction of the signal. And then we did the feature extraction by using the two different techniques, that is the discrete wavelet transform and empirical wavelet transform. And then we use the two classifiers, since it is a binary classification problem again, whether the patient is having heart disease or the patient is a normal patient. So we did the binary classification and also multi-class classification we did for the MIT-BI data set, where 5 different type of heart diseases well informations are available, and we have to detect it by using the ECG signal. And then we do the training and the testing of the classified. And once we do the training and the testing of the classified, we're trying to find out what are the feature importance using the explainable AI. So here we have used the SAP. So in most of the machine learning or the deep learning techniques, what we are doing, we are giving the input to the model and we are getting the output and we are using the output, but we are not knowing why this model is performing this output. What is the relation between the input and the output? What is the contribution of the input to the output so that it is performing better? So that can be explained by the explainable AI. And here we have used the SAP, and finally we evaluate the results by using the different performance measures. So if I explain about the data set, as I told, 3 different data sets we have used here. First is your Pascal challenge competition data set. And here we are having the ECG signal, which was recorded by the hospitals from 1 to 30 seconds long. ECG signals are there, and two set A and set B is there. And the total number of recording for class set A is 124, for B it is 312. Total number of recording is 436. And out of the total number of recordings, we have considered the 65 recordings for the set A and 266 recordings from the set B. And out of this 65 total of the recording on the set A, 31 recordings are belongs to normal people and 34 are abnormal ECG signal. And similarly for the set B, out of 266, we are having 200 ECG signal that belongs to normal people and 66 signals that is belongs to abnormal people. So similarly, in case of the PhysioNet challenge to 2016 datasets, here the ECG signals are recorded between 10 to 60 seconds long, and the PhysioNet challenge 2016 are having 6 different sets: set A, set B, set C, D, E, and F. And the number of audio signals under each set is also different. And the number of signals that we have used is 409, then 490, 31, 55. Then for the set E, as the number of signals are where large number are there, 2141. we have used only 357 number of ECG signals, and for the set F, all the total number of signals that is available, 114, we considered all the signals. And out of these, what is the number of abnormal ECG signal and what is the normal ECG signals, it is given. Out of the 409, 292 are abnormal and 117 are the normal ECG signals. And out of 490, 104 is abnormal and 386 is normal ECG signals. And here 24 and 7, 28 and 27. And if you see the set E, it is 331 is abnormal and normal is only 26. Similarly, for the set 5, 80 ECG signals are abnormal and 34 is normal. So total abnormal signals is 859 and the normal ECG signal is 597 that we consider for our simulation purpose. So as I told, in case of the MIT BIS data set, so it is having total number of recording is
Hello. Hello.
yes, madam.
Yes, ma'am. Please, can you share that proposed architecture for this one?
Okay.
Proposed architecture for the signals this you are showing.
Let me go back. Yes.
Yes, this one, sir, ma'am. Just 1 minute.
Should I continue?
Hello, ma'am. Thank you. One more thing, ma'am. I wanted to note down that GAN, how you created the GAN. So that slide, can you show? As I cannot
Let me finish, then I
note it down.
share all
Just GAN
complete
one.
slide. So
How you created the GAN, no? That slide.
So I have to go back to much back. Let me finish, ma'am, and then I will share my complete slide. So that
Okay.
Okay.
Ma'am, if you can share these PPTs, it would be really
Yeah.
helpful.
I will share. I will send it through mail to the Prabir sir, and I will tell him to circulate among all the participants.
Yes, ma'am, please. And your email ID also, ma'am. Please add it into text.
Everything is available in our website, madam. You can go to our website, ggu.sc.in, and go to the CSIT department, Computer Science and Information Technology department. You can get my profile, my mail ID, mobile number, everything is there. Everything is open in our website to everyone.
Okay, ma'am. Yeah, thank you. Very, very nice explanation and enjoying it at the background.
Okay.
Yeah. Just you share the PPTs, ma'am,
Oh,
for all
yeah,
participants.
definitely. I will send it through mail to Prabir sir, and also you can contact me through my mobile number 9098715203. I will share through the WhatsApp also to you. If you are
Just
interested.
1 minute. I will note down, ma'am. Can you tell me once again?
9098
Yes.
715203.
9098715203.
5203. Yeah. What is your good name, madam?
Saili Salkade, ma'am. I'm participant. I'm doing my research work in lung disease.
You are from which university? From Sambalpur University?
From Mumbai University, ma'am.
Okay. Mumbai University.
Yes, ma'am. And I'm also doing the research in lung diseases. So I will just see going through the
cardiovascular disease. You are doing what?
lung disease.
Lung disease. Okay.
Yes, ma'am. Okay. Thank you, ma'am.
Thank you very much. So in this MIT BIS data set, so it is 1,12,000 recordings, I think. Yes, it is 1,12,000. Total number of features is 361 after extraction. And out of this 1,75,000 patients are normal. And then it is this total number of ECG recordings are divided into 5 different classes. 75,000 are normal, Then left bundle branch block is 8071. Right bundle branch block is 7255. Then actinal premature contraction is 7129. Premature ventricular contraction is 2546. So here it is a multi-class problem, 5-class problem, and the previous 2 data sets are having only the binary class problem. So this is the pre-processing that we did over the ECG signal. So once we collect the ECG signal, so when you download the data set, you will see some bits, what I can say, the beat of the heart you can listen. If you see these audio signals, then the heartbeat you can listen. So what we have to do, we use the Python program to first read the after reading the audio ECG signal. Then what we did the resampling of the signal to 2000 hertz, right? So we resample the signal. That means we want to collect through 2000 value in every second. That is the resampling of the signal to 2000 hertz. Then we pass it through the band pass filter. What actually the band pass filter is doing, it will allow the signal is passed. When it will pass through the band pass filter, it will allow only those frequencies lying between 50 hertz to 600 hertz to pass through it, and it will block all other frequencies that is available in the ECG signal. Then we pass it through the zero phase filtering. So what it will do, the zero phase filtering. So when if there is any type of phase shifting, if any type of phase shifting is there, then when we pass it through the zero phase filtering, first once it will allow to move in the forward direction, and then it will allow in the backward direction, so that the phase shifting or the time shifting can be balanced. So that is the main purpose of the passing the ECG signal through the zero phase filter. It removes any contaminated noise from the original signal, and also it adjusts the phase shifting. Then we did the denoising of the ECG signal, because when we are recording the ECG signal with the help of the ECG machine, there may be some surrounding noise that is coming into it. It may be the hospital noise, it may be the speech signal of the technical person who is taking in the signal, recording the ECG signal, or it may be the noise that is coming out of the physiological activities of the patient also. So we have to denoise the ECG signal. For that, we have used the discrete wavelet transform to denoise the signal. Once it is done, then to recover the original signal, we have to use the inverse discrete wavelet transform. And then we did the feature extraction by using the 2 different type of technique. One is the discrete wavelet transform, and another is the empirical wavelet transform. So when we are using the discrete wavelet transform, here the mother wavelet is the DBISH, that is DB13, and here we did the 10th level decomposition to extract the features. And decomposition of the signal, when we are using the empirical wavelet transform, what it will do, it will divide the entire signal into a number of bands. So here we have chosen 5 different bands. So in this diagram, you can see the discrete, when we apply the signal, or if what is a signal, it is a vector of values, I can say. So when I am applying a vector of values to the discrete wavelet transform, what it will do, it will divide it equally into 2 halves. One is the low frequency component, and another part is your high frequency component, right? And then again, the low frequency component is again divided into, if I go to the next level, then the low frequency component will again divided into 2 halves, the low frequency value and the high frequency value. And if I want to go for the next level, that is the level 2, again the low frequency will be divided into low frequency and high frequency component, and this process will continue until we will obtain only 2 value at the low frequency component and the high frequency component. And one of the major requirement of applying the discrete wavelet transform is that the value of the vector, it must be in the form of 2 to the power n. If it is not in the form of 2 to the power n, then you have to add some 0 to it to make it to 2 to the power n. And when we will apply the empirical wavelet transform to the input signal, to the ECG signal, Here it will divide the entire signal into 5 different bands. As you observe in the right side of the screen, it is there. So we obtained the first, second, third, fourth, and the 5 different bands. It will divide the entire signal, and then we are extracting the features out of it. So these are the results. The results that is obtained by the classifier, that is the random forest classifier and the XGBoost classifier, by using the discrete wavelet transform feature extraction technique and the empirical wavelet transform feature extraction technique. And here you see in this table, it is showing when we are using the empirical wavelet transform for the feature extraction, our AUC is giving better result, that is 95.36 in comparison to our discrete wavelet transform classifier. And this is the ROC curve. And this is the SAP visualizing figure. As I told, when we are using any machine learning or the deep learning techniques, we don't know why our model is performing so better or it is performing so hard. And what is the impact of the input on the output? Which inputs are important, which inputs we don't require, which they out of the large number of inputs, which inputs are having the greater contribution, that we can find out by using the explainable AI. Here we have used the SAP. The full form of SAP is Saply Explainable AI. So here you see the figures. So if I go to the right side, that is the random forest with the empirical wavelet transform. So as I told, in case of empirical wavelet transform, we divide the entire signal into 5 different bands, and then from each band we have collected the 5 features. Some statistical features they are having. If you go to my paper, the all details are there. Now, right now I am not remembering what are the some statistical features like centroid and something that we have calculated as the 5 features: feature 0, feature 1, 2, 3, 4, and 5. And here you see the blue color is representing for the class 1 and red is representing for the class 0. Along the x-axis, the SAP values are there, and along the y-axis, the features are there. So from this figure, what I can say is the feature number 0, feature number 1, and feature number 2. These 3 are contributing more to the result in comparison to the feature number 3, feature number 4, and feature number 5 is its contribution is very negligible, I can say. Value is very small, so this can also be negligible. So this explainable AI can also be used as a method for feature selection also. We did that also in one of my paper. One of the current PhD student who is working in the field of smart agriculture, we did the rainfall prediction for the Chhattisgarh state, and here we named it as the reverse explainable AI performance, and we get it published in the theoretical and climatology, theoretical and applied climatology journal of the Spring. So that also you can do. And here, if we do the comparison of the Pascal dataset, here also we can say the empirical. Here we compare our result with the other proposed models, literature that is already published. The empirical wavelet transform with the random forest is performing better in comparison to the other models, even to the deep learning models, LXNet and VGG16, that is published in the year 2019. It is much better than the CNN also. People have used and published in 2021. In comparison to that, it is performing well. Then this is the result that we have obtained for the PhysioNet Challenge 2016 dataset. And here you see when we are using the discrete wavelet transform as the feature extraction technique, our AUC, area under curve value, is 90.48. But when we are going for the empirical wavelet transform, so here with the XGBoost, the result is much better. It is 97.44. And this is again the SAP visualization figure. So if I go to the left side, if I go to the left side of this figure, you see, this is the XGBoost with the discrete wavelet features, discrete wavelet technique features. So here, this value which is whose lines are much longer, I can say, that is 37, 54, 28, 51, 59 and 44, 45 and 50. These are contributing much better in comparison to the other features. Here, this is the result for the MIT BIS data set. That is the 5-class data is there. Here also, when we are using the empirical wavelet transform and with the XGBoost classifier, it is performing better in comparison to the discrete wavelet transform. And the ROC plot is also better in here. And what I am saying exactly want to say is that it is when we are taking the empirical wavelet transform, it is performing well in the binary classification problem and as well as in the multi-class classification problem. This is the SAP visualization for the multi-class problem. And this is the MIT BIS data set, our proposed model. It is when I did the comparison with the other published model that is published in the year 2022, you see, it is they have used the one-dimensional convolutional neural network. Then another paper in 21, it is also they are also using the deep learning network CNN. Then PNN is also there, and other models they have proposed in 2021 and 22. But our proposed model is performing better with the UC of 90.25 when we are combining the empirical wavelet transform and the XGBoost as a classifier for the ECG signal. So what are the different challenges that we face while we're doing this simulation? It is also very much important, and we should mention this also. Since the dimension of the data is very high, when it is 10 to 60 seconds, the signal is very, very large. And when we are extracting the features also out of that, it becomes very difficult, and sometimes we face out of memory of our systems not able to run the program. Such type of difficulty we face, and we have to do pre-processing is also what are the pre-processing techniques you should do so that you will get you can improve result. That is also important. And finally, we get it published in the applied subcomputing of the Elsevier heart disease classification using ECG signal and the explainable AI machine learning algorithm. So this completes my talk. If anybody wants to ask any question, then you can ask. Any question from the audience? Then I will go for that. Hello.
Hello.
Sorry. Please tell.
Yes, ma'am. Ma'am, how that gray wolf optimization you're using in DL, ma'am, directly to train the hyperparameter or any other way, ma'am?
Gray wolf optimization is it is an algorithm, sir. So it is very much similar to our GA or PSO. If I go for the PSO or GA, so you have to do the what I can say. First, you have to formulate the problem. If these are my parameters and I want to optimize, then how I can do the optimization? That formulation you have to do, and then we are applying the gray wolf optimization too. Because in case when we are conventionally using this model, there are some default algorithms which are doing the optimization. In place of that, you have to use the gray wolf optimization.
Okay, ma'am.
The complete algorithm I am not able to include here. If I can include, then it will be much better. Any more questions? Presently, I got a project from our sanctioned project from our Chhattisgarh Science and Technology on this ECG signal. So we are collecting the primary data from the different hospitals, and the title of the project is Quantitative Analysis of Cardiovascular Health for the state of Chhattisgarh. So that project I am currently I am doing. I am having a project fellow. We are collecting the primary data of ECG signal from the different hospitals and trying to implement it in the primary situation, primary environment, and try to find out how it will be effective. Many more questions from the audience? Otherwise, we'll leave.
Any queries? If not, then we'll end this session. And thank you, ma'am. Thank you for accepting our invitation to talk to come to this FDP and give a wonderful and very descriptive talk on implementation of machine learning and deep learning in a medical sector in different category. You very interestingly and engaging talk. Thank you, ma'am. Thank you again.
Okay, thank you very much, sir. Should I leave, sir?
Yes, ma'am.